A very good morning, one and all. Session number 21. In this session, we will learn about Lcr series circuit. Let's recollect of previous class. In the previous class, we have seen what is J, which is equal to root of -1, and why it is called as operator. That is, when it is multiplied with a vector, the vector rotates by 90 degree in anti-clockwise direction. In pure resistance, current and voltage are in phase. In pure inductance circuit, voltage leads the current by 90 degree. Whereas in pure capacitance circuit, current leads the voltage. The learning objectives of this session is to understand Lcr series circuit. Expression for Lcr series circuit using J operator. We will learn about impedance, the phase difference, power factor using J operator. By the end of this session, you will come to know the use of J operator in Lcr series circuit and what do you mean by impedance, the phase differences and power factor expression. Lcr series circuit. Let us consider an inductance L, capacitance C and resistance R connected from one end to the another end in a series combination to an external AC voltage, which is given by A is equal to E naught e power j omega t. In the last class, we are seeing for an alternating current, the voltage and current phase differences for pure inductance, capacitance as well as resistance. In case of pure resistance circuit, voltage and current, they are in phase. Whereas in pure inductance, voltage leads the current as well as in capacitance, current leads the voltage, which is represented in a phasor diagram as shown. Assuming that the voltage across the inductance is greater than the voltage across the capacitance, it can be written as VL minus VC or VR. The total resistance due to Lcr is the sum of the three components. One, resistance due to resistor R, and j omega L due to inductance L, and 1 over j omega C, which is minus j over omega C, that is due to the capacitance. Now, applying Ohm's law, R, which is the resistance, R plus j omega L minus 1 over omega C into I is equal to epsilon naught e power j omega t. So using this expression, I is equal to epsilon naught e over j omega t divided by R plus j into omega L minus 1 over omega C. This term can be represented as 1 over R plus j into omega L minus 1 over omega C, which is equal to alpha minus b, where alpha is given as R over R square plus omega L minus 1 over omega C whole square, and beta is equal to omega L minus 1 over omega C divided by R square plus omega L minus 1 over omega C whole square. This is alpha and beta are obtained by multiplying the complex conjugate to this expression. Now if you plot in an impedance triangle, the resistance is along x-axis, omega L minus 1 over omega C is along y-axis. Applying Pythagoras theorem, Z is equal to square root of R square plus omega L minus 1 over omega C whole square. It makes an angle theta with respect to x-axis. So using this impedance triangle, tan theta is defined as omega L minus 1 over omega C divided by R, whereas cos theta is defined as R over Z, and whereas sin theta is defined as omega L minus 1 over omega C divided by Z. Hence 1 over R plus J omega L minus 1 over omega C now can be represented as 1 over Z into cos theta minus J sin theta. This is in a polar expression. It can be represented as 1 over under root R square plus omega L minus 1 over omega C whole square e power minus j into theta. Then the expression substituting the value of 1 over R plus j into omega L minus 1 over omega C, in the current expression we obtained I is equal to epsilon naught square root of R square plus omega L minus 1 over omega C whole square e power j omega t minus theta. Or this can be represented as I naught into e power j omega t minus theta, where I naught is equal to epsilon naught divided by square root R square plus omega L minus 1 over omega C into square omega C whole square, where I naught is the peak value of the current and Z is called as the impedance. The impedance of this circuit, which is the ratio of the peak EMF to the peak current. So Z can be redefined as epsilon over I naught or ERMS or IRMS. Thus, Z, which is the impedance, is the total effective resistance offered by the Lcr series circuit. Now the applied voltage is epsilon is equal to epsilon e power j omega t, and I is equal to I naught e power j omega t minus theta. It shows that the current lags the applied voltage in a phase by an angle theta. The phase angle, the phase is given by theta is equal to tan inverse omega L minus 1 over omega C over R, and Z value, which is square root of R square plus omega L minus 1 over omega C whole square. The phase difference depends upon the value of omega L and omega C. Now let us understand with special cases. If omega L is greater than the omega C, 1 over omega C, now the potential difference across L is greater than the potential difference across C. Hence, voltage leads the current by an angle theta. Means it acts like an inductor. If omega L is less than or omega C, Now the potential difference across L is less than the potential difference across C. Hence, the current leads the voltage by an angle theta, which is given as theta is equal to tan inverse of 1 over omega L. So, omega 1 over omega C minus omega L over. However, in the third case, if omega L is equal to 1 over omega C, then theta becomes 0. Then the current and EMF, they will be in phase. For omega L is equal to 1 over omega C, then Z expression becomes Z is equal to R. Hence, the circuit is said to be a pure resistive circuit. Current is maximum given, which is given by I max is equal to epsilon naught by R, and the circuit is said to be an Lcr series resonant circuit. The average power in an Lcr circuit is defined as the product of virtual EMF, virtual current, and cos phi. The power factor of an AC circuit is given by cos phi, which is equal to R over Z, which is resistance over impedance. Note, in a non-inductive circuit, which is XL is equal to XC, then Z is equal to R, then voltage and current will be in phase, that cos R by R becomes 1, then cos phi and phi becomes 0. This is the maximum value of the power factor. So the power factor value is 1 in case of an Lcr series circuit for a non-inductive circuit. XL is equal to XC. Now if I plot all the terms expressed over here, I is equal to minus epsilon naught square root R square plus XL minus XC whole square, or epsilon is equal to I naught square root of R square plus omega L minus 1 more omega C whole square. Now in this session we learned the expression for the impedance, average power and power factor, where the impedance is given as the square root of R square plus omega L minus 1 over omega C whole square. And in special cases, when omega L is greater than 1 over omega C, voltage leads the current, whereas when omega L is less than 1 over omega C, current leads the voltage, whereas omega L is equal to 1 over omega C, theta is equal to 0, current becomes maximum. The average power, which is P is equal to EV IV cos phi, and power factor is given by cos phi is equal to R over Z, which is resistance over impedance. Quick MCQ questions. In an Lcr circuit, the vector impedance is the sum of 3 due to resistance, inductance and capacitance. The resistance offered by the inductance is called as just that inductive reactance. The applied frequency of an AC voltage is 0, then the capacitive reactance is infinity. The angle between inductive reactance and capacitive reactance is 180 degree. With an increase in the frequency of an AC supply, the inductive reactance increases directly with the frequency. That's all for this session. Thank you all. Hope you have enjoyed this.